trying to delay a little bit because today, as we try to get back onto our schedule, which I think we're going to get pretty close to today, um, we're going to kind of start with an activity today and then have a longer lecture afterwards. So I want to let folks who are going to join as much as we can. So well, I'm delaying a little bit, but I do want to get started. So just as a reminder of what we ended with last class, is now we're kind of shifting from talking about the sun to talking about other stars and how we can use what we learned about the sun to understand what's happening in other stars as well. So the last thing I showed you at the end of last class Thursday was the stellar spectrum of another star. And just to remind everyone what we can learn from a spectrum, we can learn a temperature by looking at the peak wavelength and using Wien's law, which I'm going to talk a little bit more about in a second. But first, I also wanted to just point out again that we can also get an idea of what the star is made out of by looking for these absorption features. So absorption features will tell us what is present in a star's atmosphere, what elements are present. So we can see here in this star, there's a pretty big absorption feature at this line that around, maybe like 5,800 angstrom. So that's what this A with a little dot on it means. That's angstrom. And that tells us that there's Na, or sodium, present in the atmosphere of this star. So we know there's sodium present in this star. We can also see there's this magnesium line here. So Mg, that's going to be magnesium. Folks who've done the sun lab found that they could get the composition of the sun based on where these absorption features are, which of course you can still do. Another couple little notes on notation. If you see these kind of Roman numerals next to an element, so this is O3, that means that this is an ion of that element, so it has been ionized, it's lost some of its electrons. So this is oxygen that has been doubly ionized, so O3 would be doubly ionized oxygen. Not super important, but just a little note on what that kind of means. We can also see there's calcium lines, so just get an idea of what things are in a star's atmosphere. Then we can use that peak. Like I said, we can use peak to get temperature. And I wanted to go over this briefly because there's been, I think, a little bit of units confusion. So we get a peak temperature by looking at a peak wavelength and using Wien's law. So for this, let's see what color. Okay, cool. So for this star, we can see the peak wavelength seems to be around, I said around 4,700 angstroms. So 1 angstrom is equal to 1 times 10 to the power of negative 10 meters. So there are 10 to the negative 10 meters per angstrom. So if we want to use Wien's law, where Wien's law was temperature is equal, temperature is equal to 2.89 times 10 to the power of negative 3 meters Kelvin divided by that peak wavelength. Sorry, I can't type symbols, so I'm just going to write this out. We need to make sure our wavelength is always going to be in meters. So anytime you use Wien's law, which has this temperature equal to this value divided by the peak wavelength, you need your wavelength to be in meters. So for this star, we would have T equals 2.89 times 10 to the power of negative 3 meters times Kelvin divided by 4,700 times 10 to the power of negative 10. Sorry, let me be consistent in my notation. Meters, which gives us a temperature of about 6,149 Kelvin. So just to be really careful, if you see this angstrom symbol here, that's going to be 10 to the minus 10. The other thing you might see sometimes will work in nanometers in terms of wavelength. So 1 nanometer is 10 to the minus 9 meters. So 1 nanometer is equal to 1 times 10 to the power of negative 9 meters. So those are just some useful conversion factors. On occasion, you might also see microns. So just to point this out, 1 micron is equal to 1 times 10 to the power of negative 6 meters. So those are kind of the conversion factors we might need to use as we look at wavelengths, and specifically the peak wavelengths of stars, and we use that to find temperature. Does anyone have any questions about units or Wien's law? Not seeing anything. So just as a reminder, this is just something I've seen in reading quizzes and in some of our labs. Whenever you use Wien's law, we need to make sure that peak wavelength is going to be in meters. So that might involve some conversions, either using our angstrom one, using our angstrom conversion factor here, or one of these two up here, the nanometer conversion factor or the micron conversion factor. So again, just something to keep in mind as we move forward with Wien's law. Okay. With that, I think we're going to shift right into our first activity. And so that's what, so I'm glad, so I think we've got hopefully a good number of people are here. So that's going to be, so this is our first and only activity for today. And today that's going to be our day 12 assignment called Classifying Stars. And what we're going to do in that is this building our own stellar classification system. So this is another little quiz where there's only 3 questions for this one. But the first question is kind of the big one that I want you to focus on, which is building an idea of how you might go about classifying stars. So at this link that I've given you here, you'll see there's a bunch of pictures of stars. So these kind of fuzzy pictures of stars along with their spectra. So what I want you to do, you can discuss this in your breakout rooms once I start them, is to think about what might be the most useful thing for astronomers to look for when they want to classify stars. So do you think, let's always look for how deep this magnesium line is? Is that always present? Is that something we can look for in each of these stars? And might that be a good method for quantifying what the stars are? Or maybe you think that the color of the star's image is going to be the easiest thing to find and the best way to classify them. So you might see, all of our blue stars, do they have similar spectra? That might mean they're made of similar things as well. So classifying based on color would be a good way to go. So just some things to think about as you build your system. And then there's also a few questions about how I tell you a little bit about how astronomers classify stars, both by looking at a H alpha line and by looking at colors. So you're going to try to do your best to use that to see how you think astronomers might classify the stars in that image. When we come back together, we'll go more into detail in how astronomers classify stars. So this is just for you to think about what you think is most important when we classify star systems. So we're gonna go ahead and open up some breakout rooms and have you work on this. We're gonna do this for about 15 minutes, I think, and I will be popping between rooms as usual to answer any questions that you have. Before we get started, does anyone have any questions right away that I can answer?
When I click on the link, it says access denied for the quiz
I
thing.
also cannot access the link.
The link for the link where the pictures are?
Yeah, where the questions are.
Oh, where the questions are. Okay. That might be an easier thing to fix. Sorry about that. Thank you.